In this video, we shall look at a number of examples of measurable functions, with our aim being to have a feel for which functions should be measurable and which not. Suppose that we have two sets and a function f between them. So this is the domain and this is the codomain. So far there is no question of measurability anywhere. Now I give some sigma algebra here. Now the way I shall do it is by giving a number of subsets here. Suppose I give here two subsets and I give here any three subsets. Then these two subsets will induce or generate a sigma algebra. So I consider that sigma algebra here, and similarly the sigma algebra generated by these three subsets. I want to understand when will f be measurable with respect to these things. I will quickly remind you what is the definition of measurability. That is, if I take any b which is measurable, so for all b that is measurable here, I want f inverse of b, that is the pre-image of b, should be measurable here. So f need not be invertible. By f inverse of b, I understand all the points here which map to that set b. So pre-images of measurable functions must be measurable, much like the definition of continuity, where pre-image of open sets must be open. Now when I say that I am taking the sigma algebra generated by these sets, I naturally proceed in the usual way. I look at the partition induced by these sets, which means the outside, this crescent-like set, this crescent-like shape, and this I, and this set that looks like the I. So these are the 1, 2, 3, 4 sets. Similarly here I have got exactly 8 sets. So 1, 2, 3, 4, 5, 6, 7 and 8. Now suppose I just take some point here. Now I shall not really think in terms of this definition. That is more complicated. The way I shall think about it is like this. If someone gives me a point here, and for this point someone tells me in which particular partition block this lands, then I should be able to say whether, if it is x, fx will land in which partition block here. So suppose my function is such that this x is mapped to this y, but this x prime is mapped to this y prime. Then this cannot be measurable, simply because if I tell you that my point lies in this outer thing, just based on that I cannot say where it will lie here. It may lie here if the point is x, it will lie here if the point is x prime. So this will not be measurable. The condition that I need is, whenever I take anything in this partition set, all the points will be mapped to some single partition set, like everything will be mapped to this. Similarly, if I take everything in this I, possibly that will always be mapped to this set. In other words, you can take a partition block that will be mapped to another partition block. You are absolutely free to choose how you are mapping this to that. And similarly, for each of the partition blocks, it must go to a single partition block. It is quite possible that this and this both will go to this point. That is not a problem. But every partition block here must go to a single partition block. Part of it lands here and part of it lands there, then it will not be measurable. So that is the if and only if criterion of a function being measurable with respect to a sigma algebra. Now let's take some simple consequences of this intuition. Suppose I say my function is a constant function. If it is a constant function, then everything lands inside the same partition block, irrespective of whatever measurable structure you have. So whatever sigma algebra you take here and here, a constant function is bound to be measurable. Similarly, if I take two measurable functions, in that case, is it true that their sum will be measurable? Of course, in order to define sum, in order to define something like f plus g, there must be some kind of an addition structure here, something like r or something, so the addition makes sense. So is that true? Well, if you look at it, then the result in general is not true. So if you take some f and some g, suppose f maps this here and g maps this to some other block. So if you add numbers here and numbers here, there is no guarantee that they will land in a particular block. So in general, for an arbitrary sigma algebra, that result is not true. Okay. Now let's specialize to the case where this as the Borel sigma algebra and you are working with R. So this is R. This may be anything. Now you can see that each singleton set is measurable, and as a result, such a function must have constant values over each block. So let me just clearly write it down. So I have the R with Borel sigma algebra, and here I have got any arbitrary set with some given subsets which generates my sigma algebra. Then f will be measurable if and only if over each such partition block f is constant, because in this case every singleton set is measurable. In particular, you do not need to have Borel sigma algebra. Any sigma algebra where the singletons are measurable, there you have this property. It must be constant. In this special case, f plus g will also be measurable. Because if you take a singleton here and a singleton here, if you add two singletons, you get yet another singleton. So, if you are working with from any arbitrary measurable space to R Borel or R with the singleton sets as measurable, then it is true that the set of all measurable functions are closed under addition, subtraction, multiplication, and all those operations. So this is very useful, because if I have just like continuous functions, if I just multiply two continuous functions, I get again continuous function, etc. So we have the same things for measurable functions also, provided in the codomain all the singletons are measurable.